In this question, we consider an initial value problem, which we recall is a differential equation plus an initial condition. And we see here a differential equation associated with a particular starting value or initial condition. And as we consider this, we wonder, first of all, is it separable? Because if it is a separable differential equation and it is first order, let's check that off first. It's first order because there's only one derivative, but it doesn't appear to be separable. If I bring this y over, we're going to get a horrible, horrible mix of x's and y's. So it's not separable, but it is linear. We have y prime, we have y, and there's multipliers for the y and the y prime, but they're not multiplied by each other. And what that lets us do is, remembering our new technique of integrating factors, is walk through the process for solving this as a first order linear equation. Step one is to put it in standard form. So we're going to multiply both sides here by the factor that is multiplying the y prime. And we're going to do that to both sides. And what that gives us, x times 1 over x cancels, we just get y prime. When we multiply the x into the other term, we get negative 2 over x times y. And on the right-hand side, we're going to have x squared cos of x. This is now in standard form. And so what we can do is find the integrating factor, which in this case here, our variables are y and x. This will be a function of x. And it'll be e to the integral of the cofactor of the y. And that here is negative 2 over x with respect to x. So what we get with this integrating factor calculation is we just evaluate this now. We have e to the power of, when we perform the integration, the negative 2 can get pulled out front, and we're going to have the ln of x as the integral of 1 over x. And when we get to that stage, we can simplify it by rewriting as e to the ln of x to the power of negative 2. And where does that get us? E to the ln of x, they're inverses, so we get back to x. And we have the negative 2 power out front. And we end up with 1 over x squared as our integrating factor. Next step is multiply the standard form. And it's important that it's the standard form, not the original, by our integrating factor m of x. When we do that, our standard form is here. We're going to multiply it every term by 1 over x squared. So we're going to have 1 over x squared y prime minus 2, and it's going to be over x cubed when we multiply 2 over x by 1 over x squared times y. And when we multiply through by 1 over x squared, we're going to have x squared over x squared cos of x. Cancel, cancel. Now, if we did our job correctly with the m of x, our left-hand side must, depending on how confident you feel, should be the derivative of a product. And we should be able to write it that way. So we should be able to write this as the derivative of y times something else. And sure enough, if we have our pattern of f g prime, f prime g, this is our function, 1 over x squared. If we look at its derivative, we would have x to the negative 2, bring the negative 2 down, x to the negative 3. That would be the derivative of 1 over x squared. And that means our left-hand side is literally, or can be thought of as, the derivative of 1 over x squared times y. That would give us exactly the same thing we were provided with here after multiplying through by our integrating factor. And the right-hand side is simply the same as it was before. So now we see the advantage again of using this integrating factor. Instead of having a combination of y prime and y on the left-hand side, now we have the derivative of something is equal to something else, and when we integrate, we'll get rid of that derivative and be able to solve for y. Having found this form, we then simply integrate both sides. And as we do that with respect to x, as we do that, the integral and the derivative are inverses. We end up with the function inside the brackets when we're done. On the right-hand side, we have the integral simply of cos. And what do we differentiate to get cos? We differentiate sine. And between those two integrals, we should have some plus constant when we're done. And now we can solve for y. There's simply a y here, so we have y equals, bring the x squared up, we'll have x squared sine of x plus cx squared, and that would be our general solution. Now we were given one other piece of information in this problem. We were told this wasn't just a differential equation problem, but an initial value problem, because we had a starting condition. When x is pi over 2, y should equal 3. X is pi over 2, y should equal 3, and that'll let us solve for the constant c that hasn't been determined yet. So we would have 3 as our y equals pi over 2 squared sine of pi over 2 plus c pi over 2 all squared. And we're going to solve for c. Now note that sine of pi over 2 is just 1. So that's not too bad. So we'll have 3 minus pi over 2 squared equals c times pi over 2 squared, and c will be 3 minus pi over 2 squared over pi over 2 squared. We could find a value for that, or we could simplify it in various ways, but the key thing is we have a value for it. So y equals x squared sine of x, going back to this form here, but with the c value filled in. There's our c. And that was c times x squared when we were done. And that gives us the particular solution. To our differential equation. And that's it. That's the process. Let's go through the steps again. Putting things in standard form. It has to be first order and linear. Check. Then we can put it in standard form, find the integrating factor, multiply through by it, and then what we get is a derivative on the left. Everything on the left can be expressed as a derivative of a simple product. And then we do our usual integrate and solve for y process. If there's an initial condition, we use that to identify the integration constant's value. Having done all that work, it makes sense to verify that what we have actually is a solution. We propose that y equals x squared sine of x plus cx squared. We'll verify the general solution, because if the general solution satisfies this, the particular value of c will also satisfy it. And what we want to do is verify that the solution works. So that means plugging it into the left-hand side. To accomplish that, we need y prime. Y prime will be a product rule result here. We'll have an x squared cos of x, and we'll have a 2x times c for the derivative there. Our left-hand side will be 1 over x times y prime times all this. So again, these can get lengthy, but there's nothing hard in this substitution. That's 1 over xy prime minus 2 over x squared times y, which is at the top there. So you just have to be careful, making sure you have all the ingredients. And then hopefully we're supposed to get this to simplify down to the right-hand side. So a lot of this should cancel, and a lot of it does. We have an x and an x. Actually, let's do it down here. This x squared multiplied in cancels the x squared in both of those. The x in this term, there's some x squared, some x's, so we'll rewrite that out a bit longhand. Those ones cancel. we end up with 2 sine x's. We also end up with an x cos of x. And 1 over x times that, we end up with a plus 2c. And lo and behold, notice we also have a minus 2 sine of x and a minus 2c. So yes, indeed, the c's cancel, the 2 sines cancel, and we end up with x cos of x. But what was the right-hand side equal to? It was simply x cos of x. So we end up with a perfectly valid solution. These are equal. And that means our y equals is a general solution. We'll just say is a solution. We verified by plugging in, yes, when we choose y equal to this not obvious function, x squared sine x plus a constant x squared, it satisfies this differential equation.